Hi, my name is Marianne Meyersohn, and today I'll be talking about combating the plastic crisis with sustainable polyester elastomers. So we know that the current paradigm for the synthesis of plastics is pretty unsustainable. Most plastics are derived from fossil fuels, which are non-renewable resources, and the conversion of those fossil fuels into materials like plastics can be energy intensive. However, plastics are things that we use every day in our lives and are not likely to go away. Unfortunately, once these plastic materials have reached the end of their functional lifetimes, they can end up in landfills and stay there for thousands of years, and they can also end up in oceans, harming ecosystems and ending up as microplastics, which can be found in our food. So when designing polymers, which are the materials that make up these plastics, we want to look at 4 different design aspects. The first is the feedstock. Where are these materials coming from? Can they be sourced from renewable resources like biomass? The monomer that I work with can be sourced from biomass. Next is the process, or how we make our polymers. So I synthesize polyesters, and I can do that by using non-hazardous catalysts and solvent-free conditions, so minimizing waste. The next aspect is our intended use. What are the materials that we are making? I work on making cross-linked elastomers, and elastomers are things like rubber bands or tires, and we want to make sure that the materials we are making have competitive properties compared to industrial analogs. Lastly is the end of use of our materials. Can our materials be reprocessed? Can they be recycled? Or can they even be degraded into smaller molecules that are not going to be harmful to the environment? The work that I've been doing is synthesis of covalent adaptable network elastomers. And so what a covalent adaptable network is think of a group of a lot of tangled polymer chains, and we add these small molecules called crosslinkers. And what those crosslinkers do is they form bonds between those long polymer chains so that we have a network. Now, covalent adaptable networks, when exposed to elevated temperatures, the crosslinks can break and then they can be reformed. And this is important because now we're able to access materials that bonds can break and reform compared to permanently cross-linked materials where that's not possible. And so the way that I synthesize my materials is I first start by making a 3-arm star polymer. And then I react the functional ends, or these red alcohol groups, with my crosslinker to form a covalent adaptable network, which at elevated temperatures, the bonds can exchange and the network can rearrange. And so the materials that I get look like this. They have really good tensile properties, meaning that they can be extended and will return to their initial shape. And the most interesting thing is that these materials can go from a cross-linked state at lower temperatures to a state where they start to flow at elevated temperatures. And so this is really important because this is going to enable reprocessing of these materials. So these materials can be reformed over and over again. And so with that, I'd like to thank my advisor, Mark Hillmeyer, the entire Hillmeyer group, as well as the NSF and Center for Sustainable Polymers for funding this work. Thank you for listening.